Okay, let's start. Last lecture, we had we were discussing a small signal model of a bipolar transistor, and this is the stage that we were at. We had looked at that it has three under low frequency. It has three prominent elements here: R pi from the input side between base and emitter. We have a small signal resistance R pi, which we had derived by taking the derivative as Vt thermal voltage divided by Ib, or Vt by Ic times beta. Remember, we are building this particular model for forward active mode. So without my saying it, beta means beta f, beta in the forward direction here. Okay. All right. So that's R pi. The other one is a voltage dependent current source, Gm VBE, and Gm is Ic by Vt. Ic is the DC current or the bias current flowing through the transistor. So in all of this, the capital I, capital C refers to bias and DC current. And R naught, the output resistance, is early voltage divided by Ic here. Again, the DC current, early voltage we saw in the last lecture here. All these quantities are small signal resistance, small signal transconductance, small signal output resistance here. And all the voltages that you see here are all small signal. Everything is small signal, that we should not forget. And small signal does not necessarily mean, it of course means small, but also remember the origin of small signal was incremental. So we know that there's already a DC current, a DC voltage in the circuit, and this is an additional voltage on top of the DC. Okay, so we should never forget that there is already, there's already a DC current flowing here. And this is, all this is in addition to that. Okay. All right. Now, when I said that this device, we had developed this particular model, we had developed it for a device which I had called as unilateral, in the sense that the input affects the output, but the output side doesn't have any effect on the input. For example, in this case, we can see that if I change the collector voltage, when the emitter being the reference terminal, if I change the collector voltage here, as long as I'm not changing VBE, there's not going to be any change in current. The current flowing here doesn't depend on collector voltage here. On the other hand, we can clearly see that the collector current, for example, not only depends on the collector voltage through this parameter R0, but the collector current flowing here depends on the base emitter voltage here. So the output is, that's why we are calling it, the output is affected by the input, but the input circuitry is not affected by any changes at the output side. We call such a device as unilateral. But very rarely would you find a device which is 100% unilateral. So bipolar transistor also, when you change the collector voltage here, there is a small change in the base current that flows here. Which means that if you want to build a little bit more accurate model, we need to modify, because bipolar transistor is not strictly unilateral. So the idea is as follows. If you recall, when we derived small signal model, we said that input current is a function of only the input voltage, and the output current is a function of both the output voltage and input. Now we have to modify that. So what we say is, well, the input current is a function of input voltage, Vi, but there's a small dependence on V0 also. In that case, remember we are talking about incremental model, small signal model. Any change in delta I, the input current, would be the first Taylor series expansion again, the derivative with respect to Vi multiplied by change in Vi, plus derivative with respect to V0 multiplied by change in V0. That's the first order linear approximation of any change here. This one we can show later that this is a negative quantity. So I can write this, any change, remember, is a small signal current. Delta I, when I write it, delta I change in input current is nothing but the small signal input current, II here. And this change in input voltage is a small signal input voltage Vi. We call this term as Ri, 1 over Ri. We call this term a new resistor, Ri0, let's say. Okay. We can show later on that this term is negative. That's why I put here minus V0 by Ri0. So strictly speaking, the input current that you see here has these two terms there. Okay. I can write this particular input, expression as Vi by Ri. I add a term and subtract a term called Vi Ri by 0. So we add this term Vi Ri by 0 and we subtract it also. All right. Because what we are wanting is to modify our original small signal model with the idea that there is an additional term. Now note, as I said, the dependence of this current on the output voltage is very small. Okay, which implies that this resistance Ri0 that you see here must be very large. Okay, so what we are saying then is that this Ri0 is much, much larger than Ri. Okay, so that's why if you would like to approximate, you can neglect this particular term and neglect this entire term and you get back the original model. So that's one approximation. Keeping in mind that Ri0 is so much larger than Ri that what I do is I consider Ri to be almost infinite and then we are back to the input current as Vi by Ri, the original model. But if you would like to build a next order approximation, then what we do is see if that makes sense. We can approximate we can now modify our model to this here. Note that the input current that I've written here, input current, is made up of two terms, this plus this here. If you look at the second term here, second term says Vi minus V0 by Ri0. So how do I represent? It represents by an element here. This is Vi. This is V0 here. So Vi minus V0 divided by Ri0 is this current here. Right? So it represents this. The first term says the input current is made up of a current which depends entirely on input voltage. So we represent it by a resistor. And the second term, Vi minus V0 by Ri0. So we represent it by this resistor here. Alright. Now, when I look at this resistor here, this particular one should not be Ri. I agree with you. Maybe you can call it Ri dash. But if I look at this particular resistor, what is it made up of? This resistor is 1 over Ri minus 1 over Ri0, effective resistance. If I want to write it, I would like 1 over Ri dash equal to 1 over Ri minus 1 over Ri0. I've already said Ri0 is so much larger than Ri. So I neglect it here and simply write Ri here. Now, whenever I do this, the question that often I'm asked is, well, if you're neglecting it here, why don't you neglect it here also? You're neglecting Ri0 here, right? You're neglecting Ri0 here and simply writing Ri, and then you're not neglecting it here. Why don't you neglect it everywhere? So my answer to this is very simple here. 100 plus 1. Can I neglect 1 in comparison to 100? Yes. And when I have 100 minus 99 plus 1, can I neglect the same 1? Right? I can't. So it depends on the context. A 1 can be neglected here without too much error. A 1 cannot be neglected here and you'll incur a lot of error. So when you are saying, why are you neglecting here and why are you not neglecting there? Please understand, all approximations are context dependent. We are approximating, we are simplifying. In some place, an approximation makes sense. In another place, the same approximation doesn't make sense here. So here, in comparison, Ri0, in comparison to Ri, is indeed very large. I'll not incur much error if whether I call it Ri dash or whether I call it Ri. I will not incur much error. On the other hand, if I assume Ri0 is infinite, then I won't get any element here. Then what am I talking about? Right? So this here, we are talking about Ri0 in comparison to what? In comparison to an open circuit. So earlier, when this Ri0 was not there, there was an open circuit between this and this. So in comparison to open circuit, no matter how much larger this resistance is, it's still significant. It still tells you that the output voltage will affect the input voltage via this particular resistor. But here, it doesn't really matter. Ri and Ri0, you might as well just write it as Ri. Okay? So different places, different approximations make sense. And so what we end up, if we keep in mind that our device is not strictly unilateral, then we end up getting a resistance between the input and the output, which is a resistor whose value we have to determine depending on how the input current responds to changes in output voltage. Okay? Yes.
Still, VI is less than VI.
VI minus V naught by Ri, this term, right?
Yeah, less than VI by RI.
Most of the time, yes.
So, if we are neglecting that,
As I said, I have temporarily put it there. Now note that this is Vi minus V0. All right. Let's say Ri0 for the sake of argument. Ri0 is 100 times Ri. Okay. Ri0 is 100 times Ri. So then Ri0 is 100 times Ri. I can neglect it here. Okay. Now you are asking that Vi by Ri and the two currents, aren't they much different? Won't this current be much smaller? But remember, this current is Vi minus V0 by Ri. So I may have Vi, the voltage that I apply here, let's say 1 millivolt. And then something else is connected here to this transistor, it's an amplifier, and the output, I have a voltage which is 100 millivolt. 100 millivolt. So now the current that would flow here would be 1 millivolt divided by Ri. The current that would flow here is 1 millivolt minus, let's say the output is 180 degree out of phase. So it would be 101 millivolt divided by Ri0. It may not be negligible. Okay, so this current is not simply Vi by Ri0, it's Vi minus V0. And V0 can be significantly higher than Vi here. So there are places where it may become important to include this. Okay, so what we are talking about is that if you want to build a more accurate model, then you should include this particular term Ri0 here. I agree, if you want to build even more accurate, you can, instead of Ri, you can put Ri dash. There's no problem. You can do that as well, okay? But remember, the small signal model is an approximate model already. We are already making approximations, we are calculating results which are accurate within maybe 10% error or so. Now, if this, whether you keep Ri0 or whether you don't, and it results in less than 1% error, why are you doing it when at other places you're committing errors as large as 5% or 10%? There's no point in keeping a term which is, not introducing that much error. Now, this particular term, although I've called it Ri0 in bipolar hybrid signal, hybrid pi model, it has a specific name. We call it R mu. Just as we call it R pi, we call it R mu. And again, now, a very brief explanation of where this is coming from. Why is my input current dependent on collector voltage? Why does it depend on collector voltage? We had seen in the last lecture that the collector current depends on collector voltage through early effect. So let's see here. Let's see this particular diagram, which tells you why the base current may depend on the collector voltage. So if you look at the base current here. So for us, this is an NPN transistor. The base current starts from here. And the base current supplies holes. This junction is forward biased. So the base junction supplies holes which go here. Right? Holes are injected into the emitter. So the base is the source for that. It supplies the holes which are injected into the emitter. So far we had said that the electrons which are injected, they come here. The base is very thin. The electrons diffuse across the base, reach the collector, and result in collector current. But remember, once the electrons come into this particular region here, into the base is very thin, but the base is also very rich in holes. So when an electron comes into this particular region, it finds a lot of holes. It doesn't spend much time there because it's very thin. But maybe out of 1 in 1,000 or 1 in 10,000 electron recombines with the hole here. A very small fraction recombines with the hole here. Almost like I would say 1 in 10,000 maybe. That kind. Very small fraction recombines with holes here. So this is what is shown here. That the electron which came in recombined with the hole here. So there are, if you want to be more accurate, there are at least two components of base current. One current is these holes which go into the emitter, and the other current is these holes which the base has to supply the holes which are lost due to recombination. So there is a base. So what I'm pointing out, base current is made up of two parts. In fact, there are other components as well, but I'll not talk about it. IP plus IB1. IB1 is due to recombination. So now there is a component of base current which depends on recombination. Where is the recombination occurring? It's occurring in this region that you see here, this base region here. So obviously now you can imagine the electron is coming here and it is traveling here and going over here. If the base is very large, there's a more chance of an electron undergoing recombination. If the base is very thin, there's less chance of electrons undergoing recombination. So you would expect that this base current that you see here due to recombination would depend on how large this WB is. The larger the WB, the more likelihood of an electron undergoing recombination. And we have seen earlier that this WB, the base width, depends on the collector voltage. That was the subject of last lecture's discussion, early voltage. Early voltage was nothing that when I change the collector voltage, the depletion width change, the base width change, and that causes a change in collector. So what we are saying now is, if you change the collector voltage, because of change in depletion width, WB will change. And because WB will change, IB1 will change. That very small fraction of base current that changes here, which causes a change in overall IB. Okay? So that's the origin of where this is coming from. That there's a very small amount of base current which results from recombination, and that gets affected by the collector voltage. Okay? Alright, so we'll leave it at that. Although I'm telling you that our mu is there inside your bipolar transistor. In fact, probably that's the last time again that you will see R mu. Most of the analysis will do without bothering about this particular resistor. We know it's there, but most of the time it doesn't bother us. Okay? Alright. So this is then a model for our transistor under low frequency. R mu, R pi, R mu, GMVB are not here. Okay? Now, what we have to do is, if the voltages that I'm applying here are they of course have a frequency, and if the frequencies are high, then we know that there are capacitances inside my bipolar transistor. So I need to add capacitors to this particular model to make it relevant at higher frequencies here. So for that, we need to look at very quickly what are the capacitances. Alright, so while talking about capacitance, simple reminder that anytime I have a charge in my semiconductor, charge anywhere in my semiconductor, if that charge changes with respect to voltage, I have a capacitance. Okay? If some voltage modifies the charge somewhere in my device, then of course I have a capacitance. So what we have to do is, where are the charges? So if you want to ask where are the capacitors in my device, first ask the question, where are the charges inside my device? So there are two kinds of, in general, charges that we talk about in a semiconductor device. One of them is a depletion charge, and the other one is a diffusion charge. Diffusion charge, we said, came about because of injection. When you forward bias a junction, you have injected electrons in P side, injected holes in the N side. Those are what we call as diffusion charge. Those charges made up of mobile electrons and holes. Depletion charge is made up of acceptor ions and donor ions here. So let's look at the depletion charge. We know that there's a base emitter junction here. There's a depletion region here. Emitter base depletion charge. There's a junction here. Similarly, there's a junction here. Collector base depletion charge. Now we know that as I change my emitter base voltage, this depletion charge changes. So I have a capacitance there. Similarly, when I change the collector base voltage here, this particular charge changes. So I have a capacitance there. So two capacitances we can see already. This charge will give rise to what we call as emitter base capacitance, CJE. And this charge gives rise to collector junction capacitance, CJC here. And from PN junction theory, we already know what these capacitors are. Each one of these capacitors has a form of this kind here, CJE. This is the capacitance at zero bias, 1 minus VBE by VBI. VBI is the built-in voltage of this junction here, and M, it could be half, it could be 1/3, depending on how the junction has been fabricated. Depending on the doping and other things, the M may vary here. So in order to calculate this value, you have to obtain these values from the manufacturer, CJE0, VBI, and M. So these values will be given to you. So once you're given these three parameters, 1, 2, and 3, then depending on your base emitter bias, you can calculate what is CJE. And remember, we are talking about forward active mode. So base emitter junction is forward biased. And base emitter voltage, we know that it varies, but most of the time we'll take it as 0.7. So base emitter voltage is about 0.7. So once you know VBI, then you can put 0.7 here and calculate what is CJE. Collector junction capacitance has a similar form. And you have to know these three parameters will be given to you. Although I've not shown it over here, VBI is different from emitter-based junction and VBI is different for base collector junction. So although the same VBI is used here, in general they are different. Okay. So again, if we give you what from the circuit, you can tell what is the base collector voltage here, VBC, and from there you can calculate what is CJC. So these are two capacitors that are there arising because of depletion charge. The other charge is, we said, is the diffusion charge. Diffusion charge comes about because we have injected carriers here. So when we forward bias it, we know that we have injected a lot of electrons here. We have injected a lot of electrons here. We have injected holes also here. But the holes are much smaller as compared to the electrons. So when we look at diffusion charge, when I'm talking about diffusion charge, the dominant diffusion charge is the electrons which were injected here in this particular region. Now you can clearly see if I have a diffusion charge here, as I change my base emitter voltage, if I increase the forward bias, more charge will be injected. And therefore I have a charge which is a function of this base emitter voltage here. And that gives rise to the capacitance here. Okay. So diffusion capacitance comes about because of change in diffusion charge with respect to change in base emitter voltage. So that's the dominant term here. And so we put it here in between these two because it depends on the base emitter voltage itself. So this particular capacitance is between here. And diffusion charge depends on, I'm only stating it, I'm not deriving this for you. Diffusion charge can be written as IC by VT. IC is the DC collector current, VT is the thermal voltage, multiplied by tau F. Tau F is another parameter. It's called the transit time. Transit time between the base, across the base here. So tau F is the transit time. And so IC by VT we've already seen is GM. So diffusion capacitance then becomes GM times tau F. So we've already seen how to calculate GM. So if we give you the parameter tau F, then all you have to do is multiply them together and you'll get this additional capacitance which is there between the emitter and the base. The base transit time that you see here, tau F, is, without going into too much details, tau F depends on the thickness of the base here. If base is thick, then tau F also becomes large here, WB square here. Okay. Now this also tells later on, the capacitors are the ones which slow down your device. If there were no capacitor, my device would work right up to whatever frequency that you can apply. It's only because of capacitors that devices fail at high frequencies here. So if my diffusion capacitance depends on tau F and tau F depends on the base width, so in a way it is telling you is that if you want to make your bipolar transistor fast bipolar transistor means small capacitances. Small C diffusion means besides other things, small tau F. Small tau F means narrow base width here. So if you want to make your transistor fast, you have to make the base width thinner. Anyway, that's the subject of all that would be discussed in more detail in 311. So coming back then, these are the capacitors that are there in your bipolar transistor. CJE, diffusion capacitance, and CJC here. And there's one more capacitance which is not visible here in this particular model. And that is, let's come back to this picture that I had put right at the beginning of our discussion of bipolar transistor here. So we had said that this is a simplified schematic, one-dimensional schematic. Your bipolar transistor is more like this here. Okay? So let's look at this particular picture. So this is N plus emitter here, this is the base part, this is the collector here, and this is the substrate. This is a substrate here. So we can see here, this is the junction capacitance EJE here. This is the junction capacitance, base collector junction capacitance here, CJC here. We see one more junction here. One more junction. This is the collector and this is the substrate. And we see this junction here, this particular one, between this collector and between this substrate here. Now, I'd raised that issue earlier and I didn't answer it. Why do I need this substrate here? Why don't I just fabricate my transistor right up till here and leave it there? And the reason was, so the issue was, why have a substrate? Why not make a transistor like this? There is a substrate, but the substrate is itself N-type. And then you have P and then N plus. And then in this case, there is no additional junction anywhere. I have one junction here, another junction here, and there's no third junction. So there's no additional collector substrate capacitance here. Why don't I do that? And the answer for that was that I'm interested not just in making one transistor, but I'm interested in making many transistors. So when you go back and look at two transistors, okay, when I make two transistors and I don't have a substrate terminal, then what happens? The collector for this and the collector for this is the same. The collectors are shorted together. I can't make two or three. If you make three transistors, fine. All two transistors can have their separate emitter contact, separate base contact, but the collector is the same. I don't have an isolation between this transistor and this transistor. I can't do that. So for that reason, what we have to do is, we have to fabricate it like this. We have to use a P-type here. One way of isolating two transistors are, you make the transistor, one transistor here, another transistor here. Now you look at the two collectors, this collector and this collector here. How do I go from this collector to this collector? I have to go from N to P and then back to N. So what you are seeing here is N to P, I see a junction, and then P to N, I see a junction. So we see two junctions. And then what we do is, this collector, this substrate terminal that you see here, we keep it at the most negative bias in my circuit. I look at my circuit and the most negative point in my circuit would be this substrate terminal here. Which means what? That this junction would always be reverse biased because it's connected to the most negative part. So it's always reverse biased. This junction is always reverse biased. So what happens is then as you go from this collector to this collector, what you end up seeing is one reverse bias junction and another reverse bias junction. Two reverse bias junctions. And two reverse bias junctions means there's no current flowing. So the two junctions then, this C2 and this C1 are isolated from each other. So when you're making multiple transistors on your substrate, then you have a substrate contact also, and we keep it at the most negative power and most negative voltage here. And then when you keep it at the most negative voltage here, it's a reverse bias junction, you end up getting a capacitance here also. So the additional capacitance that you get is between the collector and the substrate. Alright. So the model that I need to modify now is the following. Let's see if it makes sense. So we are modifying it for high frequency now. So we've added two capacitances between base and emitter. One is the junction depletion capacitance. The other one is diffusion capacitance. Between the base and collector, we've added the collector junction capacitance, CJC. And between the collector and the substrate. Now note, what did I say about the substrate? I said the substrate is connected to the most negative voltage in my circuit here. So usually, if I have a supply voltage +5 and -5, I'll connect my substrate to -5. And so substrate is connected to a constant voltage. And constant voltage in small signal is a short, is a ground terminal. Okay, so it's for that reason that you see here is a ground. This is a small signal model. Okay, so it's a small signal ground. And so these are the capacitors then that are there in my small signal model here. Junction capacitance, diffusion capacitance, CJC, and the collector substrate capacitance. Note that here there was this R mu also. As I said, most of the time we'll not consider this R mu. Most of the time we'll neglect that, but to be more accurate, one can put a R mu also in parallel with it. These two capacitors are in they are parallel to each other. So we just add them up. CJE plus C diffusion, we add them up and we just call them, just like this is called R pi. The two capacitors together, we call them C pi here. And again, because of terminology, we don't call it CJC, we call it C mu. Okay. So our model then becomes what you see over here. C pi, C mu, and the substrate capacitors, collector to substrate capacitors. Okay. Now, in models and in circuit design also, you will find that what we often do is we start with the simplest model. Once we understand that, then as you're saying, we are adding more elements to it. We added R mu across it. Then we added capacitors to it. This model is fine, but we would like to make the model a little bit more accurate. And one more terminal I'm adding, one more element I'm adding, and the element is RBB, a base resistance. Where is this coming from? Well, look at this particular picture here. So look at this particular picture here. This is where the base terminal is. Now the current is starting from here, from this base terminal. The current is starting from here, flows down, comes here, travels here, and where does the most of the base current go? It comes and goes here and gets injected into the emitter. So the path of the base current that you see here starts from here, goes here, comes here, and then gets injected into this particular part here. So far when we wrote all that, we didn't bother about where is our base terminal. How is the base terminal, how is the current going from the base terminal and reaching up to the junction? This is the junction here. We didn't talk about it because we had a one-dimensional schematic and we didn't talk about that. But note that as the current starts to flow from here, goes through this and comes here, all this P region is nothing but a resistor. So there is a bit of resistance between this terminal and by the time you reach the junction. There's the junction, let's say here. So there is a resistance involved, and that's the resistance that we've added. This additional resistance that you see here, RBB. Okay? And at some places, especially in high frequency analysis, this RBB becomes important. And we need to include that here. So that's the origin of this one here. Now there are other resistances also. We didn't bother about, note that this is emitter. Between the emitter contact and N plus, there is often a resistance here. So if you want to make it more accurate, you have to attach a little bit of resistance here. Similarly, note that the electrons that reach here, they go to N plus, they travel here, and then they come up here. There is a resistance involved here also. So we may add a resistance at this particular part here. So we can make things more and more accurate by adding, I've added only RBB because without that, some of the high frequency analysis results do not come out right here. Okay. So summary of the models are as follows here then. So when we will be analyzing NPN bipolar transistor circuits, finally this is what you will have to remember. That the general model in a forward active mode between base and emitter is a diode, collector and emitter, beta FIF, and most of the time when we do DC analysis, we'll assume that the diode is like 0.7 volt and IC is beta times IV. That's a simplified model that we'll use here. Okay. But at the same time, we know that instead of 0.7, we have a exponential dependence on VBE. It's just an approximation here. And we also know that although we'll use this simplified model, IC does depend on collector emitter voltage also. So although we'll use simplified models, but we should not forget that we are always making an approximation. And at some place, if you're not getting results which are right, then you may worry about are the approximations right or wrong here. And so that's the DC model, if you would like, and this is the small signal model, a general small signal model with RBB, C pi, C mu, and we've given you all the equations to calculate all the elements that are there. Equation for calculating R pi, GM, R0, all of these that are there here. Okay, C pi and all that. Again, although this is a general model, most of the time when I'm looking at low frequency, in low frequency, of course, C pi will disappear, C mu will disappear, and this also will disappear. And in low frequency, most of the time, we forget about RBB also. Because what happens is RBB comes in series with RPi. And RPi, it turns out to be usually much larger than RBB here. So we forget about RBB also. So low frequency, we just left with RPi, GM, and R naught. Very simple model. High frequency is a little bit more complicated. We need to include all of that. Model of a PNP. So this is so far all about NPN. So there's one important slide that you need to remember. The other one is model of a PNP, which is exactly same but complementary. Note the direction of the diodes reverse, the direction of the currents reverse. So it's similar, except that please do not forget the direction of the batteries here. Base emitter means emitter is now P-type and base is N-type here. So look at the direction here. Look at the direction of the current here. The small signal model is exactly the same. Same RBB, CPi, RMUs, everything is the same. Same equations, everything is the same. No difference between the small signal model of a NPN and PNP. If it's bothering you why this is still down and these are going up, we can have a separate discussion some other time on that. So okay, it will require a little bit of more discussion. But the point is the same model. Same model for PNP. In your small signal model. Same equation, same, everything is same. IC, VA, GM, tau F, everything is same. Of course, for every transistor, there's a unique set of what is RBB, what is beta, what is VA. For each transistor would have a separate set of these parameters. Okay. For saturation, as I said, our interest is in amplifiers, so most of the time we'll be in forward active mode. But if you want to check whether transistor is saturation or not, you can check with this particular model here. Base emitter junction forward bias, between collector and emitter, I have 0.2. Okay. And this is for the PNP. All right. These are I'll not go over the details. So for our course, we have developed a hypothetical transistor. We call it NE210A. All right. So it's a hypothetical transistor with these parameters here. These are realistic parameters, but all the parameters of our transistor are given here. IS, beta, beta R. Note that beta forward is 100, beta R is only 1. Early voltage 100, RBB is about 200 ohms. CJE0, CJC0, CJS, M, VBI. We have taken VBI is the same for all the junctions. VBI is here. Tau F is 1 nanosecond. So whenever we are talking about a bipolar transistor in this particular course, all bipolar transistors will have this characteristic. And based on that, these numbers then, depending on the bias condition, then we can calculate all the parameters that you see. So this you'll be doing as part of the homework. Let me just give you what the parameters are so that you can see approximate small signal parameters. If I bias my transistor at 1 milliampere, the output resistance R0 is 100K. R is 2.6K. Note the numbers 2.6K here. RBB we said is 200 ohms. GM 38 millisiemens here. CPi made up of these two terms 38.5 picofarad. C mu, this one over here, is only 0.23 picofarad. C mu is much smaller than CPi. And CJS, the substrate capacitance, is 1.6 PF. Okay, typical values that you will encounter in your analysis. All right, let me go back. And the subject of, so we are done with the models of the transistors. So from next lecture or from next tutorial also, we'll start with analysis of circuits now. Okay, so our discussion as far as devices are concerned is over. So we'll start with, so this is one of the problems from the homework. Question number 5. And in this particular problem, we are asked to calculate the note that minimum supply voltage required to ensure the transistors Q1 and Q2 operate in forward active mode. So transistor Q1, Q2, resistor 1K, VCC. This is a hypothetical circuit. Let's not bother about what it does. It is a useful circuit, but let's not get into that for a moment. And let's say you want to design this, and you want to, you don't want to unnecessarily apply 12 volt and all that. You would like to use as small a supply voltage as possible to keep power dissipation less and not to use big batteries and all that. So you would like to use the smallest possible supply voltage. But you would like to keep Q1 and Q2 in forward active mode. All of them have to be in forward active mode. And for that, you have to determine VCC and VB2. So what is our method of analysis here? So now all analysis will depend on how you deploy the models. See, once you deploy a model, then it becomes a simple circuit. It's a simple circuit consisting of resistors and all that. And so it should be straightforward. So once I look at it, remember now, even if I don't give you a beta for a transistor like this, the transistor that I talked about, we'll be discussing the same transistor everywhere. Okay. So by default, beta is 100. So if it is in active mode, if I say my transistor has to be in active mode, we know that this relationship is valid. IC is always beta times IB. So we know that IB1 is 10 microamperes. So I multiply by 100. So I get 1 milliampere. Then if I have to keep my transistor Q1 out of saturation, we know that collector emitter voltage has to be greater than 0.2. Because the moment you reach 0.2 or so, you are already in saturation. So it has to be greater than greater than or equal to 0.2. Now, for safety's sake, you don't want to go right up to 0.2. Because when you are 0.2, you may be in saturation already. Okay. But since we are asking what is the minimum voltage, so VCE1 has to be greater than 0.2 and VCE2 also has to be greater than 0.2. Both of them have to be in active mode. So both collector emitter voltage have to be 0.2. Now, 1 milliampere is there. So the current here, 1 milliamperes. And in many of these analyses that you see here, we don't bother because collector current is much larger than the base current. So we don't bother about base current much. So we say whatever is the current here, same current flows here, same current everywhere flows. Okay. So then we can write VCC is IC1 times R plus VC2 plus VCE1 must be greater than, so note that IC1 is 1 milliampere. IC1 times 1K will give you 1 volt and this 0.2. So VCC has to be greater than 1.4 volt. If I apply VCC greater than 1.4 volt, then the transistors Q1 and Q2 will be in active mode here. Now, some people may say, well, I don't want to do 0.2. I want to put 0.3 here and 0.3 here. Fine, you can do that as well. Except that in our, when we give you a quiz, when we give you midterms and all that, please take 0.2. We know that 0.2 is not very safe, but please take 0.2 so that we get everybody gets a unique answer 1.4. If people start taking different safety margins, somebody takes 0.3, somebody takes 0.4, then it becomes a bit difficult for tutors to grade. Okay. So for grading sake, use a 0.2 only. Assume that once it's 0.2 or more, the transistor is in forward active mode. Okay. So this is VCC here. And VB2, we know that this is forward bias. So I need 0.7 between here and here and 0.2 here. So VB2, we have to apply at least 0.9 volt. And then once I apply 0.9 volt here and 1.4 volt here, then I'm fine. My circuit should work in forward active mode. Okay. And, but then, so typically then, once you design something like this, that's not the end of the story. No, there is no quiz, don't worry. So what we do is, we go and do a circuit simulation. See, these are simplified results, right? I've used simplified model, 0.7 volt, and I said when you go up to 0.2, the device is not in saturation. So the next thing is to, not in a exam, but in real life, the next thing is to go ahead and simulate your circuit and see whether the circuit is working fine or not. So this is our 210 NP and BJT here. I'm going to forward this particular file here. So when you look at this 210 BJT here, the model is over here. all the model that you see here, all the parameters that you see, we put it here. So this is our transistor. And in this transistor, let me do a analysis of this one, which is called DC analysis. And in DC analysis, when I do that, what I'm doing is VCE, the collector voltage, I'm sweeping from 2 to 0 at intervals of 0.01. So I'm changing the collector voltage, and I'm looking at the collector current, just to show you the transistor characteristics, okay? So let me run it for different base currents, okay? So that's our transistor. If you don't want to see it for all the base currents, so one can do and see stepping, and one can remove, stepping the base current, one can remove it. So one gets here. Now, you can use a tracker. All right. So let's look at this one. You can see here it looks flat, but there is an early voltage. You can see that the current is changing. This shows you the current here. So you can see here the current is changing. Right? Where does saturation begin? Maybe right here at this point. Saturation begins here. So let me take it there. Where does it begin? Well, where would you say? Not really 0.2, right? We are saying it's beginning at 0.228. At 0.2, you're somewhere here. Already into saturation. So it's not really, what we are taking is not really correct. We should take a little larger. Okay? And then if you go further, then you see this is what happens. All right. So anyway, this is our transistor. Let me see if I have the circuit that I just made. Question number 5. Yeah, this is the circuit that we made. Okay, this is the design that we did. We did this design with Q1, Q2, 1K, and we said with 1.4 and 0.9, it should be in active mode. Okay, so how do I check active mode? Well, when you do analysis, it's called dynamic DC. Dynamic DC means that as you change any component value, it will immediately tell you what the consequences are. So let's do dynamic DC here. It says at what temperature do you want to carry out analysis? 27. So let's keep it at that. It gives you all the voltages everywhere. So note that it's not really 0.7, it's 695. All these things will be a little different. But let's see here. All right. You see this point here on. It tells you whether the transistor is on or not. And it also tells you whether the transistor is in saturation or active. This particular simulator for active mode, it calls it linear. Okay. So let's see on. It says both are in saturation. Both are in saturation. So when we designed it, we took what? 0.2. Right? We took 0.2 and we just saw from the transistor that 0.2 was not really accurate. So if I redid my analysis here, instead of 0.2, if I took, let's say, 0.3. So this would be 0.3, this would be 0.3, so I get 1.6, right? So let me put 1.6 then. Instead of 1.4, I can change here. 1.6. And note that if this is 0.3 and 0.7, so I should change this to 1 volt, maybe. So both of them are now in linear mode here. So both of them are in forward active. So what it is saying is you may be making assumptions, but then when you actually go and simulate, you may find that things are not working, and you will, in real life, you'll have to go and make some corrections, especially if you're pushing the boundary. We went right up to 0.2, and it's not fair to go right up to 0.2. We know that transistor is already very close to saturation. So 0.3 was better, and with that, things are fine here. All right. Okay. So let's stop here.